Welcome to this lecture on partial differential equations. Today, we are going to explore a powerful technique called reduction to canonical forms. If you have ever looked at a complex equation and felt completely stuck, this is the tool that will help you untangle it. We will learn how to shift our perspective to make impossible problems incredibly simple to solve. Let us start with a simple analogy. Imagine you are trying to measure the exact width and height of a picture frame hanging on a wall. If the frame is tilted at an awkward angle, keeping your ruler strictly horizontal and vertical will mix up your measurements. The smartest thing to do is simply tilt your ruler to align perfectly with the frame. In the world of partial differential equations, we frequently encounter equations that are mathematically tilted. The variables x and y interact in messy ways, making the equation nearly impossible to solve. Reducing to canonical forms is the mathematical equivalent of tilting your ruler. Now that we understand the goal, let us look at the mathematical structure. This is the general form of a second-order linear partial differential equation in two variables. Here, u is the unknown function we want to find. The capital letters a through g are coefficients. The most troublesome part of this equation is the term with the coefficient b. This is the mixed partial derivative, where we differentiate with respect to x and then y. This mixed term is what tangles our variables together. Our primary goal in reduction is to find a way to make that b coefficient become 0, simplifying the entire equation. To figure out exactly how to tilt our mathematical ruler, we rely on the characteristic equation. Notice that this quadratic equation only uses the coefficients a, b, and c from the highest order derivatives in our original PDE. By solving this equation for the derivative of y with respect to x, we discover the characteristic curves of the system. You can think of these curves as the natural highways along which information travels in our specific equation. The roots we find here will tell us exactly how to define our new, custom-tailored coordinate system. Before we solve an equation, we can classify its behavior using the discriminant from our quadratic formula, b squared minus 4ac. Just like in basic algebra, this value tells us what kind of roots to expect. If the discriminant is positive, we get two distinct real roots, meaning the PDE is hyperbolic, behaving like a wave. If it is exactly 0, we get one repeated real root, making it parabolic, like heat spreading. If it is negative, we get complex roots, and the PDE is elliptic, like a steady electric field. This classification dictates our next steps. Let us see this process in action with a classic problem, reducing the wave equation to its canonical form. We are given the second derivative with respect to x minus the second derivative with respect to y equals 0. Our first step is to identify our coefficients by comparing this to the general form. We have a hidden 1 in front of the x derivative, so a is 1. There is no mixed term, so b is 0 and c is negative 1. We plug these values directly into our characteristic equation. Continuing with our hyperbolic example, the middle term disappears, leaving us with a very basic algebraic equation. Taking the square root gives us two distinct real roots, positive 1 and negative 1. This confirms our discriminant is positive. To find the actual equations for our characteristic curves, we integrate both of these simple differential equations. The constants of integration give us the expressions y minus x and y plus x. These are the tilted rulers we were looking for. We assign them to our new Greek variables, psi and eta. Now comes the transformation phase. We must rewrite our original derivatives in terms of our new variables, psi and eta. We use the multivariable chain rule to find the first derivatives, u sub x and u sub y. But our original equation contains second derivatives, so we must apply the chain rule a second time. This gives us the expanded forms for u sub xx and u sub yy in our brand new coordinate system. Notice how this process naturally introduces mixed derivative terms in the new variables. We finally have all the pieces. We take these new expressions and substitute them back into our original wave equation. Look closely at what happens when we distribute the negative sign. The pure second derivative terms cancel each other out perfectly. The only things left are the mixed derivative terms, which combine to give negative 4 times u sub xi eta equals 0. Dividing by negative 4 leaves us with our final canonical form. This incredibly simple result tells us the mixed derivative is 0, which is trivial to solve by integrating twice. Now, let us tackle a slightly different scenario. We want to reduce an equation that has a messy mixed derivative term right in the middle, which we desperately want to eliminate. As always, our first step is to identify the coefficients of the second-order terms so we can build our characteristic equation. By comparing to the general form, we see that A is 1, B is negative 2, and C is 1. We plug these coefficients into our quadratic formula to see exactly what kind of roots we will get this time around. Continuing with our parabolic equation, the characteristic equation simplifies to a perfect square trinomial. Because the discriminant is exactly 0, we only get one repeated root, negative 1. We integrate this single differential equation to get our first new variable, psi equals y plus x. However, to create a two-dimensional coordinate system, we absolutely need a second variable, eta. The rule for parabolic equations is that we get to choose eta ourselves. We just pick something simple that is independent of psi. The easiest choice is usually just setting eta equal to y. With our new variables defined, we once again use the chain rule to find our derivatives. Because eta does not depend on x, the math simplifies beautifully. The first derivative u sub x is simply u sub xi. We then apply the chain rule again to find our second derivatives. Taking another derivative with respect to x is straightforward, giving us u sub xi xi. We carefully compute the mixed derivative, u sub xy, and finally the second derivative with respect to y. We now have all the transformed components ready. For the final step, we substitute all our new second derivative expressions back into the original parabolic equation. Let us expand this and group the like terms together. Watch how the terms interact. The u sub xi terms combine to exactly 0. The mixed derivative terms also combine to exactly 0. Every single complicated term vanishes, leaving only one term behind. This gives us our final canonical form. What started as a messy, tangled equation has collapsed into a single, beautiful, easy-to-solve statement, proving our choice of variables was perfect. Let us visualize what we just accomplished mathematically. On the left side of this diagram, you see the solution plotted in our standard x and y coordinates. It looks like a tangled, overlapping mess. The complexity comes from looking at the equation from the wrong perspective. On the right, we see the exact same system after our coordinate transformation to the xi and eta grid. By shifting our perspective, the tangled behavior straightens out completely into a simple, clean line. The geometry perfectly matches the physics. You might be wondering why this entire process matters in the real world. The truth is, solving raw partial differential equations is often mathematically impossible. When engineers model the stress on an airplane wing, the vibration of a bridge, or heat distribution in an engine, the raw physics equations are incredibly messy. By reducing them to canonical form, mathematicians strip away the geometric clutter. This allows us to apply standard integration techniques and reveals the true physical nature of the system, proving definitively whether it will oscillate, diffuse, or settle. Let us summarize what we have learned. Reduction to canonical form is the ultimate simplification tool for second-order partial differential equations. By solving the characteristic equation, we discover a custom coordinate system that perfectly aligns with the natural behavior of the equation. This transformation systematically eliminates the difficult mixed derivative terms that tangle our variables. Ultimately, it turns complex, unsolvable problems into standard templates that are easy to integrate and understand. You now have the tools to untangle these equations yourself.